fructose, monosaccharide sugar. You're sweeter than a woman's kiss.
Question here. There we go. Okay. Is we want to know. We want to know if a certain treatment affected the presence of E. coli in cattle. The special treatment they gave was 2 different types of diets, and I don't know much about this part of it, but I know that the control diet had no distiller's grain in it, and then the treatment diet had 25% DDD distiller's grains, which I don't know exactly what that means. But the reason I did that is because it's becoming more popular. It's a byproduct of ethanol production, and so it's being used more in cattle feed, and so they wanted to see what impact this diet had on the cattle. So the study used 5 cattle in each group. There was 5 treatment cattle and 5 control cattle. And in the beginning of the study, they did not have any E. coli present, and they measured that to make sure. And then they inoculated them with the bacteria and then measured throughout the next 6 weeks to see what happened. So when they gathered their samples is where the poop comes in. The samples are gathered through fecal samples. And 3 times a week, samples are taken, and they are measured, and I won't get into the details about that, partially because I don't know all the details. It's not completely relevant.
I know what inoculate is, but some people might not know what that is. Would you mind explaining that?
Give the cattle E. coli, basically.
Yes.
Okay, they infect them with the bacteria. Sorry, thank you. Okay, so after they've been infected, I believe they waited 3 weeks, and then they started taking their measurements. And that just gives them the time of making sure that they actually have bacteria in their system. So they take the fecal samples. They, like I said, 3 times a week they take these measurements, and each time they take a measurement, they want to take 3 samples on 3 plates. And the way they actually see if it's present is they just physically count the number of colonies that they see. And so I'm sure there's some kind of solution that puts on there, and again, I don't know the details on that part. But they physically count the bacteria. And so if they're looking in this sample and they don't see any bacteria, they say, well, 0 are present, okay? And then the question is, well, was there actually 0, or was this sample just not showing bacteria? And that was the main question that I was interested in, is what do we do about this? Is it actually a 0, or is it something different? Okay. What this graph is showing us is the theory and the understanding, the accepted idea is that every day when I take these measurements, the presence of the bacteria will follow a distribution like this. So what this means essentially is, it's called a log normal distribution. I'll say that here now. But the height of the bars show the frequency. So the taller the bar, the more often that happens. And essentially what's happening here is those smaller measurements occur a lot, and then as the number of bacteria increase, that doesn't happen as often. And this isn't a graph from the data, it's just showing the distribution. So we have a lot of small measurements. We don't have a lot of very big measurements, which hopefully kind of makes sense if you think about this when you're inoculating that. You gave them the bacteria, you should expect to see something there. Okay. So log normal distributions, which will come in handy later. But the main question is, what do we do if nothing's present? Okay. Well, nothing's present can come from a couple different things. Maybe there actually is nothing there, and they didn't see it because there's no E. coli present in that sample. Maybe there's nothing there because the sample they took just doesn't show it. Maybe there's nothing there because it's just too small of an amount to actually see. And that's what this limit of detection has to deal with. It's exactly what it sounds like. There is a limit where they can't detect values smaller than that. So this looks very similar to the last picture, but if you imagine taking this distribution here and then just getting rid of those lowest, smallest values, you just physically can't see them. And so, like, erase those guys, tear those out, you're just missing that part of the distribution. So we still assume it follows log normal, we're just missing some parts here, and this is kind of where all the mystery happens. We don't know if those are actually 0, if they're just really small and we can't see them, or what the deal is with that. Okay, so that's one problem we have with the study, is we can't tell what values are occurring if they get too small. Another problem we have, or this is actually a way they deal with that, sorry. The way they deal with that is they do what's called enrichment. So they take their samples, didn't see anything in them, record this as 0, and then the enrichment process essentially is just overnight they get to incubate some more, and the next day they recount. If nothing is still present, they said, well, there's no E. coli here, it's a true 0, and they keep it as 0 in their data set. If something is present, instead of counting how many colonies they see, well, there must have been something, is what they say. And so if there is something there, coli must have been present, they record just a 1 is their default number. They figure that's the lowest there possibly could have been. And if there was nothing, it stays at 0. Now this wouldn't really be a problem because it fixes the missing data and it's fairly reasonable and it's what's done, it's very accepted. But the issue with this is if you think back to a log distribution, okay, from a statistical viewpoint, this is a problem because most statistical analyses require normal data, so bell-shaped data. And this isn't bell-shaped. And the very common acceptable fix is to do what's called a log transformation. So you take the logarithm of every single value that you had, and what that does is it basically stretches this distribution out so that now that peak occurs in the middle and your tails are a little more symmetric. And that's what statistically we want to see. But the problem with doing that is when they go through and they fill in these zeros for something was not present, you can't take the log of 0. It's just mathematically impossible to do. So they have these zeros in their data set. They have to take the logarithm of them. They just can't do it on some of these values. And so what the practice is to do is ignore the zeros for a little bit, take the log of everything else, and then just carry those zeros over. Okay? Which is kind of a big problem mathematically. I won't go into explain it, but if you think backwards, that causes all sorts of issues. So that's another really big problem here, is the way they do their enrichment. Okay? And there you go. Can't take the log of 0. Okay? So what I look at, and this is from my master's report, that's why I keep saying what I did and what they did. I did this from my master's report. Is say, well, how do we fix this problem? What can we do differently with this missing data? And I looked at a lot of different things. Okay. The simplest thing you can do is say, well, if it was missing and I didn't see anything, let's just count it as missing. Okay, not a 0, just completely missing. The problem with that is, if you're just going to count the stuff that you have complete cases for, if you only have 5 samples in your treatment group and 5 samples in your control group, and it turned out about a quarter of it had missing data, you're reducing your samples down to like 3 cows in each group, and that's not good. Okay, so that's not a good way to go about this. Okay, and that missingness is due to some kind of reason. It wasn't random. It's because those values are small, so it has some meaning behind it. So you can leave it as 0s and 1s, which is what they do. The problem with that is we run into the problems with logarithm, so it's not the best thing. So then another option you can do is you can say, okay, well, if a 0 is a problem, why don't we just put a 1 in for all the zeros, since that's the smallest thing we could have observed, and then do the analysis. We don't have the problem with log of 0. Reasonable, but now you're inflating all your values. Some things actually are 0. Now you're counting them as something. All of your numbers are going to be too big, and you don't want that. You want to try to get accurate representations here. So these last 3 things are kind of what the research suggests, and those are what I've did most of my focus on. Research suggests these 2 things here. You can take the smallest value you saw and divide it by 2 and put that in for all of your missing data. So that way you're kind of accounting for the fact that it could be small, kind of accounting for the fact that it could be larger, but you're fixing that problem taking the log of 0. And the second one here is similar, dividing by the square root of 2. Again, similar idea there, just kind of gives you a different number you're imputing for all those. Okay, and the last thing is multiple imputations, and this is kind of the highest level of what you could do. It's the ideal thing. Essentially what that does is based on information you have from your data, you generate random numbers that should fill in the holes that you're missing. The problem is it needs big data sets, and this wasn't one, so that really wasn't done. Okay, so what we're going to say is, okay, we're going to try out these different things and see what works best. We plug the actual data into these statistical models, filling in those holes with all these different options, and then we run them and see what happens. Okay. So when you're done, you get out a bunch of numbers, and I didn't put those numbers here. Okay, it's pretty boring to look at a table that has, there were 3 models and 14 methods and a whole bunch of numbers for all those. So I skipped that. But the thing is, you get all this stuff out, and you still don't really know what worked best because you don't know the truth. You don't know what was actually missing there. So the way we usually do in statistics, we say, okay, that's what actually happened. To decide whether that was best, we're going to run a simulation. And what a simulation study does, it says, okay, here's my actual data. Let's try to make new data that has all the same features, the same means, the same amount of variation, the same count, and all that sorts of stuff there. And you make this new data set that doesn't have any missing data. Okay, so you have complete data, and then you go through and you say, okay, let's take out some data to make it match up with what I have. I know what should be happening now because I have a complete data set, but we're going to kind of ignore that for now so we can see how our models do. So I looked at 14 different methods for handling missing data, and those are the things like we talk about over here, okay, leaving 0s and 1s and doing all sorts of stuff there. So 14 different ways to deal with that. 12 different combinations of how I actually made the data set to make it match the original data, so like changing means or changing, the amount of variation you had and stuff like that. And then 3 different actual statistical models to run for that. So there was 504 combinations of things that we looked at in this study. So it was a lot of stuff to keep track of, and again, I'm not giving the numbers for there. But basically what we found out was that the best thing to do, based on what we saw with these simulations, we ran the simulations, we looked at the results, and then going back and looking at the original data we were missing, we were able to see what matched up best with that. And the best thing that these people can do when they're inoculating these cattle and trying to figure out the thing with E. coli is to keep doing enrichment as they do. Okay, so take your measurements, record them as zeros. If after enrichment there's still nothing there, keep that 0 there. If there is something, keep it as a 1. That's just fine. Okay? Or not keep it as a 1. Do this part here. Impute the minimum divided by square root of 2. Okay, that turned out to be the better than just imputing a 1 or imputing some other number there. You're going to put a, and I forget exactly what it turned out to be here, but you can put that number in place of the 1s. And then to fix the problem with the logarithms, you still can't take the log of these zeros, is we bumped everything up. And we just added 1 to all the values, and then we can take the logarithms because 0 is gone, and then we can go through and do the rest of the results there. Okay? So that was the best that they can do there, which isn't really what they were doing, but hopefully kind of continues from there. So all that, what they had hoped to see. The control cow that had no distillers grain in their diet had a lower presence of E. coli.
Hey, Paul.